Hello, I'm Nirmala Shenoy. I'm a professor at Rochester Institute of Technology, and I'm using this presentation to uh, present some of my thoughts on the evolving internet architectures and challenges. What I'm planning to do through this set of slides is just walk you through the revolutionary growth of the internet and some of the pillars fostering the growth of internet. We then next look at some of the foundations of networks, which are predominantly the network protocols. And then I will touch upon the increasing energy consumption and carbon footprint by the IT industry, which is a serious concern. And then I'll identify some of the challenges and the severe imbalance in all the technologies that are contributing to the growth of the internet, and have a look at, well, what is driving this situation, and are there some potential solutions? So let us start with network architectures. Okay. So there were the days of the native local area networks, and then came the internet, the advent of the internet. So that is a typical picture of a local area network from yesteryears. And with the advent of the internet, which connected all these local area network, came the internet service providers. And the internet service providers introduced a tier-based architecture to define their business relationships. Meanwhile, cellular, wireless, and satellite networks were growing independently. They had their own architectures. Then came the days of the data center networks, which was an evolution from our mainframes. And then came the content delivery networks. And these content delivery networks were introduced primarily for fast multimedia delivery, but they are taking over all the services today. And Internet of Things, not to miss out on that. And there are numerous limited domains also that are cropping up with their own architectures. Some of them have their own addressing schemes. Now, if we look at the growth of the network architectures, there seems to be a revolutionary growth over the past few decades. We can identify a revolutionary growth here. But looking at all these networks, which form part of the internet or they are connected to the internet, what exactly is the internet architecture today? So it's very difficult to define the internet architecture today. Next, let us look at some network topologies, that is the connectivity among the networking devices. So we started off with bus, ring, star, and mesh, partial mesh topologies. And then we went on to more structured topologies like the three-tiered core, aggregate, and access network type of topologies. And then came the topologies where there was a need for high availability, redundancy, and symmetry, like folded clause, DCell, hypercube, etc., that are being used in data center networks. So that is what you see coming up at the bottom of the screen now, okay? And besides these growth in the network topologies, this trend came around of underlays and overlays and underlay over overlays and things like that. That is very predominant nowadays. Meanwhile, not keeping aside the wireless networks, wireless satellite networks and sensor networks, they can probably have an arbitrary topologies. Typically, satellite networks have a more structured topology. But trying to summarize on this, if you look at today's networks, they have a structured topology. They're not just arbitrarily put together. If I look at the growth in the network topologies or the evolutions in this, it doesn't look so revolutionary, right? So let us look at some of the technologies that have contributed significantly to the growth of the internet. First among these is the silicon technology. Okay, gone are the days of the 2x1-inch chips. And today, not only do we have CPUs, we have APUs, GPUs, and dedicated processing unit for different processing needs. The processing speeds have grown tremendously. So have the memory storage capabilities. They are just phenomenal. And we currently even have chips in tiny cards, which are throwaway cards, as tiny as you see in that little pop-up there. Then let us look at some transmission technologies. We started off with twisted pair cables, then came the coaxial cables, and then came the advent of fiber, which was really revolutionary. And there was a huge, significant advances that were made in both encoding and modulation techniques. And meanwhile, the same thing can be said about the wireless transmission technologies as well. These have been truly phenomenal. They have increased not only in capability, but they are available at very much reduced cost and very low energy consumption. So, trying to look at the growth of the internet, the pillars of the growth of the internet, you can identify to all the technologies that we just went through. It's been phenomenal. Okay, now let us look at the foundation of the internet. And to me, the foundation of the internet are the network protocols and the algorithms underlying these network protocols. It is a bit murky at times with numerous protocols all being put together and combined together. We hardly see any innovations here. So let us look at it now. Network protocols, primarily from the internet perspective, okay? Again, let us start with the native LAN days when we had token bus protocols, token ring protocols, Ethernet, CSMA, CD, and so on. And nowadays it is more like contention or no contention. We just seem to be using carrier sense multiple access anyways, okay? The TCP IP protocol suite was invented 40 plus years ago to connect all these different native local area networks. The internet operations are primarily governed by the IP addressing scheme, and sadly, the IP addresses were allocated or assigned without any logic or structure. Okay. And if you look at the routing protocols, they also use the IP addresses to locate networks. Needless to say that because of the arbitrary assignment of the IP addresses and so on, the routing protocols are also quite complex. Okay, continuing with network protocols, let us look at some advances we made. I'm not mentioning ATM and the cell technologies that was introduced by Cisco several decades ago. They somehow had a premature death, but what emerged out of that was a multi-protocol label switching, which had a dependency on the internet protocol. While ATM did not survive, MPLS survived, which was in a way derived from the ATM technology. In the multi-protocol label switching, there was one major problem. We had to reserve paths and so on. So we wanted to avoid that. What did we do? We introduced segment routing, which is a kind of source routing. When specific operations were required, all that we did was we just took whatever protocols were available off the shelf and combined them. We would tunnel L2 through L3, L3 through L2, and so on. That is the type of innovation we have been doing. Let us take an example of data center networks. They have very structured topologies, but guess what? We still use IP addresses, which are supposed to be assigned in an arbitrary manner. And we took Border Gateway Protocol, modified the AS numbers, and when we needed load balancing, we used ECMP. And when there was a need for link aggregation, we combined the LAG protocol with these other two protocols. By the way, BGP runs on TCP, and that adds on to its complexity. So, how about the operational complexity when you aggregate all these protocols? And in turn, what is the impact on the energy drain? Data centers are supposed to be consuming quite a bit of energy, as I will be showing you in the next couple of slides. Another protocol, spanning tree, which was invented quite some time ago, it had some serious problems. It was not good enough. So what did we do? We just borrowed the Dijkstra tree implementations in ISIS and incorporated it at layer 2 and layer 2.5. There are others, of course, I'm not mentioning everything here. So trying to summarize here, what are the innovations have we seen in network protocols, especially for the internet? There seems to be a complete lack of innovations here as far as I'm concerned. One more thing it is very important to mention here is there a study of complexity in network protocols? That seems to be completely missing. I've been looking around for it and never came across much research being done in this area. As we aggregate these protocols and so on, it would be good to know how many cycles of operations are we increasing, how much of memory storage are we increasing, what is the increase in management, how complex is the troubleshooting. Okay, especially when we aggregate the protocols. Looming ahead, serious energy concerns, and I mean really serious, okay? Energy and carbon footprints escalate as IT industries grow and computational complexity increases. Despite the significant energy conservation that we are achieving due to the great advances in chip and transmission technologies, here is a snapshot of the electricity used by data centers, which supersedes what entire countries consume. A great example of this serious energy concern and carbon footprint. The growing size of networks and increase in operational complexity seems to supersede all the benefits of these fantastic chip technologies and transmission technologies. Other challenges which are looming ahead is difficulty in management, a need for automation because trying to configure all these multiple protocols get more problematic. Troubleshooting is getting difficult, right? And the solutions that I came across to cut down on these serious energy concerns were use artificial intelligence to selectively shut down or micro data centers with energy harvesting. But fundamentally, what we are not addressing is the computational complexity, which we seem to think is not really contributing to the energy consumption. What about security and privacy? This is sidetracking a little bit, but important to this discussion. Security and privacy challenges, we all know, continue to increase. The TCP/IP suite was not invented with security in mind. The layer 3 and layer 4 protocols are full of security holes, as we all know. And what do? Whenever these hacks come up, whenever these challenges come up, we just put a patch to it. We are not addressing the root cause for these problems, which are these layer 3, layer 4 protocols. Okay, what we really need is solutions that look at the big picture and not point solutions, which seem to be the way that we are going. Who are the contributors to any research or innovation in this area, that is network protocols? They are the researchers from universities, research labs. We have the maximum flexibility to come up with innovative ideas and test them out. But guess what? We are continually under the pressure of publish or perish fear, as I call it, because publications or grants for that matter based on revolutionary ideas are not received well, nor do they get published out there, nor do we receive grants. So how do we incentivize these researchers? Industry, they are the other contributors. They have their own agenda. They have to market their products. They have to get there first. And I don't think they are bothered too much about the path or process on getting there first. So whatever protocols you get easily off the shelf, well proven, just let us take it and put them together. That is the trend that is being adopted today. How about the standards bodies, the Internet Engineering Task Force? It seems to be all about IP. Even if you take a solution-based solution for the internet, not the internet protocol, even if you take a solution for the internet to IETF, they are not very comfortable with accepting such ideas. What is missing? We should stop these tug of war among ourselves. And we should have an open mind to work together to embrace and foster revolutionary clean slate and green solution. Talking about clean slate and green solutions. Well, they do demand that there be a backward compatibility. There's a need to address backward compatibility with the Internet protocol. They should be incrementally deployed. You can't just deploy a solution throughout the Internet. You can test it within a network in an autonomous system and then another network and so on, and extend it to the whole autonomous system. We call it incremental deployment. So we can test it and see, well, it is able to work with IP and it's working well. Okay. It should work in parallel with IP. Okay. It should embrace different emerging networks, some of them like the limited domains, which are pretty challenging, and they are going to continue to evolve and grow. And they should also allow for future growth. Now, are these all impossible to achieve? Not in my opinion. So here comes some clean slate green research that we are pursuing at the Lab for Networking and Security at the iSchool at RIT. One of them, I call it as the expedited internet bypass protocol. Obviously, it's a replacement for the internet protocol. You can bypass the internet protocol using EIBP. Okay. The question we asked ourselves is, do we have to continue using the internet protocol suite? Networks have structures. They're not arbitrary like they were once upon a time. They're not arbitrarily put together. They have a great structure. So let us use them. Or even if they don't have a structure, let us overlay a virtual structure. Okay. So here is an example of a commonly adopted 3-tier structure in most networks. Okay. We can use this structure to auto-assign structured addresses that capture the positional information. The beauty of such an approach is, as you just noticed in the picture that just came up, these addresses, they carry the route information. What we have done here is we just configured the core addresses just with some tiered addresses, and all the other routers in the distribution layer and the access layer, they derive multiple routable addresses from the routers to which they connect at tier 1. As simple as that, okay? There's no need for routing protocols, no need for open shortest path first or any of those other routing protocols to establish routes. We get multiple routable addresses and paths without loops. And this works with IP. It is a fully tested protocols. We have a set of publications at the end. And this can also be incrementally deployed, first in one network, extend to another network, and so on and so forth. The next idea that we are working on is a mesh tree protocol for data center networks, because data center networks are growing in a big way. Data center networks currently use a combination of BGP and ECMP predominantly. Okay. But if you look at the structures adopted by data center networks, they adopt highly symmetrical structures. It is easy to assign routable addresses to define non-looping paths using these symmetrical structures. And we use what is called as virtual IDs for that purpose. These virtual IDs are auto-assigned and they define paths. Again, no need for a routing protocol. Do we need BGP and AS numbers for this? We don't need them at all. There is the picture that came up, and here are the virtual IDs. You know, the mesh tree starts from the TAR as a root, and the branches just go right up to the spine without forming any loops, and they are all auto-assigned, okay? The basic C code for the executable for this mesh tree protocol that we developed for data center networks was just 42 kilobytes. Publication list, you're welcome to look at it, and thank you for your time.